middle school chemistry, so we're going to call it MSC, Unit 8. And the topic for this unit is going to be chemical reactions. And so we're going to cover a couple basics today as far as chemical reactions go. What you should understand is that in biology, chemistry, things like that, chemical reactions, even in biology, are really important. For instance, the way that our blood takes in oxygen and puts out CO2 is a really important process. Some of the chemical balances in our body are really important. There's chemical reactions taking place all the time. As you get further in science, you realize that physics, chemistry, biology, they all start to blend together because they all rely on each other for information. There's physics processes in our body, there's chemistry processes, and then there's biology as well, the study of our anatomy and the cells and things like that. So chemical reactions are kind of this building block. And so what we're going to do hopefully this week is we're going to unpack what is a chemical reaction, how do we read a chemical reaction, what are some of the intricacies of it, and then we're also going to break down like what are the 4 major types of chemical reactions. Nothing too complicated, mind you. All right, so the first thing we're going to do is we're going to look at how we write them. Okay, it's very similar to a mathematical equation with a few differences. So let's go ahead and get started. Let's look at a chemical reaction for CO2, okay? Let's look at a chemical reaction for CO2. First of all, if you were to take pure carbon, okay, so we're going to call this carbon, and let me zoom in on this a little bit. If you were to take carbon and you were to add to it oxygen, it would produce CO2. All right. This is what we call a chemical reaction or a chemical equation. Now, we can also write this in terms of words. So we're going to call the next one's going to be a word equation. And the word equation is going to be carbon plus oxygen gas, we're going to get to that in just a minute, produces carbon dioxide. And we know it's carbon dioxide, all right, so it's a single carbon and 2 oxygens. Okay? So that would be what we would call a word equation. Can you freeze it? Yes. It just has to be incredibly cold.
What do you call ice? Oh,
okay, so there's a word equation. Now, there's another way to look at this too, and you would hear this kind of expressed, but we would say that 1 part carbon and 1 part oxygen gas reacts to produce 1 part CO2. You know, that's what we have to get to. No, it's actually 1 part oxygen gas, but I will show you why that is in just a minute. That's an excellent question, and I'm going to come back to it. Okay? And you should take heed of those kind of questions because they're very good. Okay. All right, so this is kind of a key idea. All right, so what we see happening here is this. If we had to count up, and I'm going to just, is it okay if I go to a new slide here?
That's fine.
Okay. If we have C plus O2 reacts to produce CO2, okay, listen to what I'm saying. C plus O2 reacts to produce O2. We're going to call these things on the left-hand side reactants. They're the things that react. That seems pretty simple, straightforward. If they're on the left-hand side, they're reactants. They're coming together to produce something. So what do you suppose we call this over here if we're producing it? It is a reaction. The process is a reaction. It's not a reactor, not reacted. When I am selling something, what am I selling? A what? A product. Okay? I mean, some people do sell produce. I mean, that's true. Supermarkets, farmers, things like that. This is what we call a product. Okay? It's the end product. We have two reactants that are combining through the process of a chemical reaction to produce a single product. Okay? We have two reactants producing a single product. Look at the way I worded this. 1 part carbon, 1 part oxygen gas. That's a total of 2 parts. So we have two things coming together to produce 1 part CO2, one thing. So is carbon the same thing as CO2? No. Is oxygen gas the same thing as CO2? No. Carbon is totally different. Charcoal would be carbon. Coal is carbon. O2 is a gas. It's in this room. But when you take the two individual products, the two individual reactants, and you combine them through a chemical reaction, they become something totally new. Okay? So I want you to kind of even put that chemical reactions are the processes by which chemicals are combined to produce, keyword here, new chemicals. Sometimes all we're combining are elements. Sometimes it's more complicated than that. But basically you're taking chemicals, you're combining them or taking them apart. Chemical reactions are the processes, or is the process by which, I should say process, single. Chemical reactions are the process, no, it's plural, by which chemicals are combined, and I'm going to even have you, or broken down, because they can come apart as well, to produce new chemicals, different chemicals. Yes, Mr. Martin.
You can have more than 2 reactions, right? Like you can.
Oh yeah. Sometimes some things will go through a series of what we call chain reactions. There's one, and then it leads automatically into another, and then leads into another. Mm-hmm.
Is it like, you know how in math there's commutative property?
Yeah, sort of.
Like you can put all over the place.
Well,
does it have to be in a specific order?
Not necessarily. For instance, let me cap this kerosene because it smells. Not necessarily. For instance, if you wanted to switch the C and the O2 so that the O2 came first, that would be fine. However, the C and the O2 have to be on the left-hand side of the arrow. They cannot be on the right-hand side of the arrow. So we are side-specific here. However, you can move things around like a commutative property, sure. So I could write this as, in theory, O2 plus C reacts to produce CO2. That would be fine. Okay? We typically, when it comes to the periodic table, we try to write things as they appear from left to right. So carbon appears before oxygen, so I would typically write C and O2. There really isn't a preference. It's really your personal preference in that regard. However, the arrow does indicate something important here. It does indicate that the direction the process is going. Okay? So when you were if you were to look at this, you would say, oh, O2 and C are combining to produce CO2 because the arrow is going from left to right. If I were to flip it, to trick you, I'd have to flip the arrow. But you should be able to read the direction of the reaction by the arrow in the chemical reaction itself. Let's look at another example of a reaction, okay? Because that's going to be the important part. Let's look at the reaction for water, okay? So, water is actually formed when hydrogen gas and oxygen gas combine, okay? Hydrogen gas is what we call H2, and O2 combine, and they produce H2O. Let me he gets to the core of the issue. Chemical reactions have to follow one basic property of nature, and that is that matter, periodic table, all of the elements that make up everything in the entire universe, you cannot lose matter. You cannot create matter. You cannot destroy matter. It has to be the same amount of substance on the left and right. Different chemicals, mind you, but you have to start with the elements you start with have to be the same elements you end with on the right hand side. So I have two hydrogens. Oh, where'd my tools go here? Yeah, they're there. I have two hydrogens on the left-hand side, and I have two oxygens on the left-hand side. Okay? But on the right-hand side, I have two hydrogens, so that's good. But I only have one oxygen, which means that if I were to look at this reaction in real life, I would say, oh, I've destroyed an oxygen. The universe dictates that's not possible. Okay, you have to account for every atom. So that means in order to get this to what we call balance out, we have to manipulate the chemicals. This is how that looks. I start to put numbers out front. I'm going to put these numbers in red, okay? So I would do something like this. I'd put a number out front, and I'd put a number out front here. Now, this comes with practice. I'm placing those twos very specifically. I'm going to put a 1 here, okay? These are what we call coefficients. What it does is it changes the quantity of the atoms we're working with, okay? So instead of 2 hydrogens, I'm now working with 2 H2s. It would look like this. Instead of 1 H2, I have 2 H2s. So instead of 1, I have 2. And I'm adding to that 1 O2. So I'm going to call that O is much larger. O2. And over here, I have now 2 H2Os. So I have an oxygen with 2 reds, and I have an oxygen with 2 hydrogens. Okay? Now, do I account for all the atoms? I had 4 red circles, 2 green circles. On the right-hand side, do I have 4 red and 2 green? I do. I do. Okay? Whereas before it was this. Okay? But that leaves me with an extra what? Yeah, is there anything on that oxygen? No. So it's not actually working. In order to produce solid H2O molecules, I have to have 2 H2s. But because I have 2 H2s, I end up with 2 H2Os. So hence the reason that at the top I have 2 H2s plus 1 O2 gives me 2 H2Os. It gives me a grand total of 4 hydrogen, 2 oxygen, and on the other side, I end up with the same exact thing. 4 hydrogen and 2 oxygen. It's a multiplier. Does that make sense? It's a multiplier.
So it's kind of like invisible.
Yeah, well, in most chemical reactions, we would write it. But what we do is we determine what that is. Basically what you do is you go through and say, where can I add numbers so that it works? Okay, we're going to actually play around with this tomorrow. I have an app that I'm going to pull up, and we're going to put in numbers, and we're going to try to make things balance out. Yeah.
So, whenever you're writing a chemical reaction like that and you're using oxygen, is it always O2?
It's always O2. There are certain chemicals on the periodic table that have to exist in pairs. We call these diatomics. And you're going to hear this term again. Diatomic, meaning 2 what? Atoms. literally diatomic, 2 atoms. I mean, it's not tricky here. It's not code words. Okay, so there are certain things, because scientists have observed them. It's not because we made up the rule. They say, hey, there's weird chemicals out there. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Iodide. No, I didn't. Iodine. These chemicals, somehow, some way, somehow, whatever, hydrogen too, they exist in pairs naturally. Just because God designed them that way. They just they exist in pairs. So because they exist in pairs, that's how we have to use them in chemical reactions. So O2 and H2 always come in a pair. They never exist by themselves, because that's the way that they were designed. So this is how we have to look at this. Let me do another one here. Or let's go back to our carbon example. Does the carbon dioxide example need any coefficients? Why? Because I have how many carbons on each side? 1, so that's good. And how many oxygens on each side? 2, so the number's already balanced. So I'm good. So there'd be a 1 and a 1 and a 1 as my coefficients. I don't need to balance it out any differently. All right, but let's look at a different chemical reaction. This one is going to be, this is a good one. This is one that you guys are actually going to perform in the classroom with an acid. Okay, so this one is going to be HCl plus Zn produces, let me go ahead and move this over a little bit. HCl plus Zn produces ZnCl2 plus H2. Okay, so the real question becomes, okay, what I would recommend you do is in trying to figure out where a coefficient should go, make a list on each side. So I'm going to make a list here. I'm going to go, okay, I have hydrogen, I have chlorine, and I have zinc. And on the other side, I have the same thing. So I'm going to draw a line. And over here, I have hydrogen, chlorine, and zinc. So the question is, how many do I have on each side? On the left-hand side, how many hydrogens do I have? Okay, I have 1 hydrogen. How many chlorines? I have 1 chlorine. How many zincs? 1 zinc. Boy, you guys are just nailing it. All right. Hydrogen on the right-hand side. 2 chlorines. 2 chlorines because it's Cl2. How many zincs? 1 zinc. If it was 2 zincs, there'd be a little 2 after the zinc here, but there's not. So there's a law, conservation of mass, states that there has to be the same number of atoms on both sides. Is there? No. Now, I can't even begin to explain how important this is. I cannot change the little numbers. Those are there because that's the way those chemicals have to combine. I can only put coefficients in, and right now the coefficients are as follows. The coefficients are 1, 1, 1, and 1. But we know that doesn't work because the numbers don't match up. So what I need to do is I need to double the hydrogen and double the chlorine on the left-hand side. How do I do that? Put a 2 where? If I put a 2 in front of the HCl, okay? Okay, if I put a 2 out front, it multiplies everything in that chemical by 2. So it works for the H and the Cl. So if I put a 2 here, it's really saying I have 2 H's and 2 Cl's. It's actually the distributive property. So all of a sudden, I go to 2. Do they match up? They do. And now what I would say is that my chemical reaction is balanced. And when it's balanced, it is accurate. And when it's accurate, it's the natural way this reaction works. This reaction is really cool. Do you guys remember the little balloon I filled with gas? And then I blew it up? That's this reaction. Well, at least mine looks like balanced. Balanced. I mean, that's actually a C in there, so. That's,
Isn't zinc a metal though?
zinc is a metal. Yeah.
And isn't chlorine?
HCl is hydrochloric acid.
Yeah, but isn't that an ionic thing because it's metal and non-metal? No, hydrogen's not a metal. Oh, yeah, that's.
Acids are a little different too.
But
Zinc chloride.
it makes zinc chloride.
Zinc chloride dissolves in that substance, so it appears to be in there like salt dissolved in water. And H2 is a gas, and so it escapes. And so that's what I trapped in the balloon, and then I lit on fire for a secondary reaction to produce water.
So zinc chloride is an ionic compound.
Zinc chloride is an ionic compound because it's got a metal.
But then it shouldn't have a, what's it called, the little numbers.
It can.
But you said ionic compounds don't.
They do. For instance, they just have to.
You don't write them whenever you're writing them up. You don't put the dyes or the.
Right. So this is. You're right. There's no prefixes in there. So it's zinc chloride. Because it's ionic, there's no prefixes. Okay, so we're getting some. Yeah, it takes time to put all the pieces together. Okay, takes time. Do we understand the basics here? This is how you write a chemical reaction. They have to be balanced. You're taking chemicals, you're combining or breaking them down to produce new chemicals.